So hello, to introduction to Sandstar, I have Calvin Slater with me. How are
How's it
you,
going?
Calvin?
I'm Calvin Slater. I'm a end user. I work for Automated Logic dealership, but I'm highly interested in open controller technology. I think that open controller technology is the future of our industry. I mean, um, there's a lot of great products out there now, but in the future, I believe, a lot of the stuff, the level of interoperability uh, increasing, where you can have multiple vendors. It's just going to happen. I mean, you look at the success of like Tritium, and the main thing that made Tritium successful was that it talked to a lot of systems, and what I think will happen is that will reach all the way down to the to the field controller level. The field controller, you'll be able to. It's kind of a scary thing. Somebody can walk up and program your controller, but I don't think that it necessarily be something to be afraid of. I think as long as you're an integrator and you're taking care of your customers and making them happy, they're not going to be you're not going to have to worry about some other company coming in there and taking over your sites. I think they're going to appreciate the fact that their facility is truly theirs, because that's what I hear from a lot of customers and consultants is, I've got hundreds of these field devices in my building, and I can only go to you guys to program them. And I really don't like that. I want open programming tools. I want to be able to do anything that I want with my building. And as long as you provide those products
Hmm.
and do a good job, we're going to continue to use you. And so a lot of people just don't want to be locked in anymore. They have a big expensive facilities to manage, and they don't want to have to be stuck with a particular
Hmm.
vendor. And that's coming from a integrator that is selling a product that's, I mean, it's not you're not closed product, has
Hmm.
backnet. But I think a lot of people are discovering that we need to go further than backnet. We need to go to even more. We can share networks now, but now we have to be able to program each other's controllers. And
Hmm.
the scary thing, but I think it'll really open our industry up.
Really cool. It was a great intro. So, when you heard about Sandstar, why did you? What made you? What interests you to get involved with
Well, I mean, I've always been interested in open controller frameworks.
it? Hmm.
Uh, Ever since I saw, I met the people who did EasyIO when they're first rolling out their product,
Hmm.
and they brought it to our dealership, and we're an ALC dealer, and I didn't really know what Sedona was, and I kind of didn't understand it, and I didn't pay attention to it. But then all of a sudden, like, people were really interested in their products, and they really started to take off. And that's the reason why, is because you have a FG controller, and it's your controller forever. You don't have to, even though
Hmm.
you'll probably get a company to help you with your site, like, it's yours. You have the tools, you have everything you need at the end of the job to do anything you want with your site. And their controllers became extremely popular. And then also, I heard about Haystack, just like everybody else. And that's a really nice idea too, because one of the major difficulties anybody has when even sometimes when you come up to your own site, you don't know what's there.
Hmm.
Um, and it only makes the job a lot harder if you have to find out what work other people did before. And, a lot of the times it's your own company. You have a site. Some people did work there years ago. They've retired or moved on. Nobody knows anything about that site. Wouldn't it be nice if there was some type of database containing all the data someplace where you could just, pick up where you left off, is kind of thing. Another interesting thing about Haystack that I see some people doing, the direction is going towards, is commissioning. If we standardize what we call things, then, instead of having a technician, paying them hundreds of dollars an hour to sit there with a commissioning agent, the commissioning agent, if they were using a tool that was using that standardized data, the commissioning agent could do certain aspects of checkout himself. I mean, if you call a valve the same thing and everybody agrees what's a valve called, somebody can take a tool like SkySpark and they can pull up all the valves on the site and they can cycle them all open and closed. Then you've saved a lot of time and money, because usually it's us who have to pay for one of our technicians to sit out there and to cycle the valve while the commissioning agent checks it out. It's a very unautomated process. It's very time consuming and expensive. Commissioning is very, very expensive aspect of any job, especially, new construction.
I completely agree with it. So do you want to explain the architecture? I will just share my screen and we can just go through what Sandstar is in technical terms, and then we can just go into a demo of it. So here is the Sandstar architecture, and from what you have seen so far from code, do you want to explain the architecture that is in here and what it means for other manufacturers or hobbyists for using the Sandstar?
Well, first, to start off, just a really short comment on hardware. From the late 2000 time period, when like flash memory became affordable to put in embedded devices, a lot of our field controllers, VV boxes, fan controllers, the zone controllers, the unitary controllers, were based on lower end devices, microcontrollers, right? A microcontroller, when you build a microcontroller, you're trying to build one single device, and you have to use the same process. So, you can only fit so much, RAM and flash on there, and you can't put an operating system on there, and you can't have like tons of memory allocations, like if you can't do the live programming thing, right? Unless you have lots of memory, you have a memory manager, kind of like when you're on a JACE, you can do the live programming and then save it, do a whole bunch of stuff and save it. You can't do that on a microcontroller because microcontrollers just don't have the resources. Up until recently, now with a lot of the developments in like smartphones, the price and availability of these processor, the capabilities going up, and the amount of resources that are available to these devices are up, and the price of these things is going way down. I mean, we're almost at the point where these things are just totally dirt cheap, and there's no reason to use microcontrollers before, because that was the only reason that we're stuck with microcontrollers was price. So now a lot of these new platforms that even the big manufacturers are coming up with, like Distech, Siemens, everybody they're all kind of standardizing on a hardware platform that has an operating system. And of course there's pitfalls to devices that have operating systems. I mean, everybody remembers back in the 90s, their Windows would crash, all the time. And the same thing is with an embedded device. You're always taking that risk is the instability, because I mean, you're just you have more and more code. So that can be a kind of scary thing too, but it's just something we're going to have to get through, because it's the way of the future. All of these new devices have operating systems, and they're not just doing that to be reckless. The reason is because these field devices, these field controllers, I've heard the term edge device, you're just going to have to do more. your device is going to have to serve up metadata about itself. Your device is going to have to be live programmable. Your device is going to have to store data, for a limited amount of time in the event of, if you have like outages or bandwidth issues. You can't constantly be taking that zone temp and shooting it up to your server wherever it is. And you have to have that ability to possibly store some of it so that it can deliver it to the server later on. I mean, that's a lot of people talk about for the analytics thing to happen. It all starts at the very low level devices. It starts at the unitary controller, at the fan coil unit. And the good news is that we can make unitary controls now at a price, and they're already on their way. Unitary controls that have the ability that you can basically, kind of like a cell phone. Cell phones used to have firmware, but now if you want to add a capability, you add a little bit of hardware and you add an application that runs on an operating system. And that's how all of these devices, that's the direction that all of these back and electrical devices are heading. They're going to have OSs just like your phone does.
Yeah, and Linux has become very stable lately. There's Linux instances running without any issues for years.
And then the real-time kernel is slowly making its way into becoming the kernel, right? So kind of an important thing is going to happen with an operating system is, if you're controlling like a piece of machinery, like if you have a VFD drive, you're going to have the ability to have real-time system calls. So if you have some kind of application that's controlling a time-critical piece of equipment, that thread is going to have to run before any of the other stuff has to run. So it's going to have to multitask. So it's going to have to be, VFD speed. Okay, serve that HTTP request. Do this, do that, but only after my DDC control thread has run. But those capabilities are already there. It's just architecture, right? You just have to make sure that your hardware and software architecture supports that. And there's nothing wrong with that. The people who work on Linux have been anticipating that people would be doing things like this with their operating system for a long time now, and it's been working its way into the kernel. So I mean, so if you can do that
in the Linux 9 plus, there's a new cape manager to manage the GPIO and I2C devices, and there's a whole new framework that has been improved. So let's get into the Sandstar layer. Do you want me to explain, or do you want to join in the conversation? We can do.
I'll just ask questions along the way, because I mean, there's a lot I don't understand yet. I mean, it's what you did is awesome. That's really cool. This is exactly what we.
Basically, what we're doing in Sandstar is that we're combining pretty much three different applications into one. One of them is Haystack, the other one is Sedona, and in order to link that with the Linux operating system, we wrote a Sandstar engine. And the goal of the engine is basically to read the data from different devices. And in order to abstract it, we created basically a CSV file called device template. And that basically abstracts different types of devices to a simple term called a channel for the Sedona engine and the Sandstar Sedona engine, Sandstar engine and the Sedona virtual machine to understand. And in between, communication of it is done through IPCS, which is pretty much a standard within Linux, which you can pass data in between processes, inter-process communication system. On top of that, we have the POCO web service, which is right now a proven web service that's written in C++. And we can basically do haystack calls. This literally enables us to create a Sedona configuration file that is pretty much hardware agnostic independent. And it enables us to move the code as long as your input IO count matches between manufacturers. And also there's a potential to add historian within it, and you can pass the historical data out through the Haystack web services to applications like SkySpark, or any other web service wants to consume that historical data, they could consume it. So as an architecture, it is seamless architecture. There's only one process that starts up, and within that process, there's multiple processes, and that's pretty much it. So any questions that you have, Calvin?
Yeah, can you talk about how the so from what I understand is you start off with, and the abstraction of the IO is really cool. I mean, that's a big deal. You know, one thing that everybody's going to want to be able to do. I mean, and you're able to do this. Some of this is kind of a thing that we talked earlier, but we haven't talked about this yet. An important capability for any group of DDC products is the ability to take a program that you like and that's proven, just take that DDC code and without doing anything, run it on another device. An example of this, right? Say I'm using a little 5 input, 5 output controller to control an exhaust fan. So I create my super duper, bulletproof exhaust fan program. And then, all of a sudden they add like a whole roof full of exhaust fans. So say I have now I've got like 20 exhaust fans. So I want to, upgrade this controller to a, like a super duper, expandable device where, I have all these inputs and outputs, but I don't want to rewrite my DDC code. Of course, an exhaust fan program is going to be pretty easy to do, but maybe something else, maybe a chiller program. Your points change, and you're gonna move around hardware, and you're gonna make changes. An important ability is to take the DDC that you have, and without heavily modifying or completely rewriting the code, take that DDC and run it in another platform. Now, one of the problems with there's some products out there where you write DDC code and you can't run it in another platform. You have to completely rewrite the whole thing, basically, because a lot of these things will compile into a binary, which is meant just for this particular piece of hardware. There's no layer of abstraction, right? So that's kind of a cool thing. This was never really a problem with Sedona. Sedona is awesome. It's like the greatest DDC code ever, in my opinion. I looked through it. But one of the things is if everybody, like actual hardware IO, like the GPIOs, the analog inputs, the outputs, you have to be able to take your DDC application and throw it on another machine. You either have to abstract those things, or you end up coming out with your own flavor of Sedona, and that's really kind of what has happened with Sedona up until this point. Is a lot of different people have come out with different Sedona-based products, and they're all really nice. But the thing is, when it comes to the stuff that all controllers have, inputs and outputs, they kind of created their own implementation to work with their hardware, which is fine because that's what you have to do if you want a controller. But you can't take somebody's application, so like every Sedona application has a schema, and the schema is basically kind of like in Tritium. It's like the modules you're using, and one of those modules is going to be hardware related. So for every particular controller, you're going to have an I/O module, and it only works with that platform. So I write all this DDC code, and I can't take my code from this controller and throw it at another Sedona controller, because you have to be using the same kits. And that's one of the things that really stood out to me about about Sandstar is you can, well, not theoretically, I mean, you've done it, you can abstract the I/O. So you can take a program from platform A, and you can throw it right on platform B. And you could even, I mean, with Sedona, you can do whatever you want. You can put multiple instances of a DDC program. So I can take that exhaust fan program and I can put 10 of them on there. I mean, even though this, we're not there yet, but it is possible. And that's kind of the thing that like DDC tools need to have. You need to be able, like cross-platform, multiple instances of a DDC program, because sometimes you're going to use one controller for several pieces of equipment. And not all products have that, and it's all architecture dependent. It's dependent on hardware and software.
Yeah, so your explanation is really good. Having a hardware independent Sedona code will definitely get us to move to the next level, where everyone will benefit out of it. Especially, we will be able to create data-driven applications more so than ever. And there are other benefits too that we can go and deep dive into it. Do you want to get into a demo now?
Yeah, yes, please.
Okay. All right. So the idea, what I will do right now is that I will split the screen into two, and we are going to go into views of this application and explain you what we have. What we have here and how it is basically seen on the graphical interface area. So the interface that you see is SkySpark right now. It is very tightly knit with SkySpark, but Sandstar area is pretty much agnostic to SkySpark. We're just using the interface for maintaining the GUI and runtime, start, stop, and also generating the database thing. So let's start with the database template and what it is. So there's an area called ADC config, and we're going to click on device template, and it's nothing more so than just a CSV file. And you can see the CSV file's first column is the channel number, and these will be defined by any manufacturer, and each device type will have a different numbers inputs or outputs. However you define it will be up to you. So basically, when you look at channel 32, digital output 1, it is nothing more so than a system call to the Linux system. P811, which is the jumpers on a BeagleBone, is used and has within the cape, and the cape is something like this. Within the cape, it basically says BO1 is P811 on the Linux system call, and it's a digital out. And the trigger event is on 4 to 5 within the address. So the idea of the hardware abstraction is that you want to map the system calls to a number, and we call that number a channel. So literally, we are defining ports of a controller as channels, pretty much. So any question on this that would interest you, or anything in this part? Calvin?
No, I understand. So far, I'm a big fan of BeagleBone. when you made your first video for control trends, like I think you showed something like this, or it's in the PDF, and I was like, hey, those are BeagleBone pins, like and that's that's an abstraction right there, right? Because on the Setara processor, all the way down low, all of those pins are an actual pin on the BGA of the Setara processor, and it abstracted from the hardware level to Linux. So Linux, goes all the way down, and it knows like how to turn on the hardware. Because of course on either a microcontroller or SoC, multiple pins or balls on the BGA can represent multiple signal outputs. So it's kind of really the same concept with Sandstar, is where you can take a single input and you can configure it in different ways. Like of course on a DDC controller you can have a universal input where it can be 4 to 20 via DO, and you have to do that on a DDC controller, and same thing with an embedded system. So I mean that's really cool. Just take that concept of being able to change hardware and abstract it, through all the levels of hardware and software, all the way up to your DDC application.
Yeah, that's a great comment, actually. So within the input one, we do define it as an analog initially, but when you define it within the database Zinc, you can actually make it a binary input as well. So the inputs are actually universal inputs, and the initial load of configuration within the abstraction can be analog, but you can change that to a digital, and we will get into that as well. So within the device config, so now we're talking about the device Zinc file. And what you are seeing is a Zinc file, and very creative naming by Brian Frank and the creators of Haystack. Zinc stands for Zinc is not a CSV. So although it is kind of a CSV, but the only part of it is that within the first row, there's more data that is typed. Haystack as a language, Haystack is pretty much all the data types are typed. What typed mean for everyone within the listeners? Type means is that a data type, a bool or number or ref are written differently so that the program can differentiate what it is. When you look at a CSV, everything is a string. An application wouldn't know if it's a number or if it's another data type. Within Zinc, when you write it down, you know what the data type of it is. So when you read and write, you don't have to interpret what it is. So it gives us a lot of flexibility by having that. And within the header area for each table, you can actually would know what these are. So actually what I will do is I will look at this data set that is stored as a model within the Folio database. It is actually nothing more so than device or device ref. So it is basically the table that you see here, and for each channel we have a record. So it is basically for each row within that Zinc file, we are defining a port, a channel of the controller. That's pretty much how the engine gets loaded. It basically looks at the database Zinc for each row, which has the channel number. And once it sees the channel number, it knows how to make the system call for that specific device by going to that channel. Then we have the Sedona code. We are going to get into that. There's another abstraction layer that we basically utilize within haystack tags. So let's dive into it. One thing is that a creation of a device zinc, you can do it manually like this, or you can basically, if you had the whole time within the world, you can try to write it here, but it would not be feasible. There's the complexity layer. Defining your channels is the complexity part of it. So for that, what we have written, which is, this will be free all the time. We will not be charging for this application. We call it Record Editor, and it will run within SkySpark, and you could try to run it in everywhere else. It's written in HTML and JavaScript. What this is you have basically device, and you're defining each port of your system. And what we will do today is that we are going to delete a zone temperature, and we are going to regenerate it together. And do you have any question, Calvin, from here? I'll just give you
no,
to catch up.
I understand it completely. You know, I just learned recently, you know, what a zinc and a grid means, because I just started, you know, to really start looking into haystack. I might just you know, talk about it briefly. The reason, you know, you look at the CSV and there's a lot of information on there, but the reason to have a grid is you're going to have a lot of you know, well, in this case they're physical points, you know, the channels, and the grid is there because, you know, you're going to have your channels, which are the rows, and then you have the columns. Not all channels will have data available for a particular column. So it's important to point out, like, you know, you saw all that text. You have to organize your data in a way that a machine can consume that data. And for it to do that, it's, you know, just kind of like an Excel spreadsheet. It's going to have to look for a certain attribute, and then for every single channel, you're going down that particular column, and you're saying, you know, so like the current value for every single channel. And you know, a grid in the form of a zinc is an important element of haystack. You know, it is a data format that is not CSV, but it's an extension of CSV. You know, it's like where you have CSV plus, right? You could call it CSV plus. It's a data format that a machine can consume and manipulate. You know, so like like a, you know, SkySpark or other tool can take this data and it can organize it all, and once it knows what's there, it can manipulate the data, which is, you know, another thing that's coming up, right? That you're going to show.
Exactly. So yeah, from what you mentioned, that not all the rows or not all the channels will have the same column information. So we're looking at the cool column, which is a marker, and it has cool command stage 1, and this one exists here. So you can actually see that it is within there as a data only on that given channel. So let's go into Record Editor. Let's delete the zone temperature and regenerate it, and this will explain why we created the Record Editor. It will give an idea for listeners. And what I will do is, there's also, this one is within the Folio database. When you see it in red header, this is in Folio database, and when you click here, we actually move into the real engine. So what we are going to do is, you can see that this is red now because it doesn't exist on the Folio level. On the SkySpark level, I'm just going to delete this here as well. And we are just going to go back here and we're going to add the zone temperature within the application right now. So the way we add a channel is that we just go on the left menu and we add a channel. And the channel, we need to know what the channel number is. And to make it easier, you can actually just go to the device template, and we had deleted it from channel number 4. We are going to add the input number 1 to the device. So here's channel number 4, and we are going to give a nav name. Nav name is actually a great tag within Haystack community as what the point name is. So we'll just give a zone temp and then we'll hit accept. You can also have in here, this macro will give us the channel. So we can actually have channel here and then we can put it in parentheses. So this will actually type our channel number as 4. So we can just save this here and save. And you can see that now we created a zone temp and our channel is 4 within parentheses. Now, the next part is that there's a graph network behind this. And the graph network, let's just go to Graph Commons website. This is really interesting website. And we're going to just search in here as Sandstar. And within this, we have a Graph Common site. We actually utilize this. What this does is when we have a device that has point marker, it starts suggesting us tags. And these tags are layered. They're compounded from each other. And we're literally adding this to one point. So here's how it works. So we have a kind tag, and we can add a number. So this defines the application's data type, programming data type. Now we are going to define the channel's port type. So this will be an analog and input. The first layer of suggestions are complete. Now we are getting to the second layer, stages of layer of suggestions. So now we are going to add Fahrenheit. And Fahrenheit is not only a unit. It's actually utilized within the Sandstar engine as our conversion variable. So if you are in Canada or any other part of the world, if you're using Celsius, then it would actually convert the raw data coming from GPIO by utilizing this unit tag. And
yeah, that's important. That like that's really cool. I want to comment on that. So going back to the hardware, when you have a physical point on a controller, basically it's just going to be a voltage or a current that's going to go into that input, and that it eventually becomes voltage because all analog to digital converters are based on voltage. But basically, there's going to be an ADC sitting there, right? And that ADC is going to have to take that voltage, and it's going to spit out a digital value, which is called a count, an ADC count. Now from there, that's the only thing that the hardware knows is what the count of the ADC is. So if you're in, if you're in the United States or if you're in another country, and you basically have to have some kind of table in your hardware that is going to map the ADC count to your unit, right? So you're going to have a table or some kind of scheme where you have your ADC counts, and then you have your Fahrenheit values, and then you might as well create another column that is the Celsius values. So if you're able to give the device that information, then instead of pulling from the Fahrenheit side, it's going to pull the Celsius, and then that you'll be able to configure the device from there. I mean, of course, there's all different ways you can do it. Like you can just do a direct conversion from Celsius to Fahrenheit, but it's usually a more efficient just to take straight count, go straight to the value instead of trying to do some kind of conversion in software, you know. And if you can tell the device what units you're using, then it'll go straight to it and get it, you know. That may not be like a good example, but like conceptually that's where it is right there. Is, you know, instead of converting or doing anything in software at higher levels, you just get the value directly
from tagging. So the next part is basically we defined the port, we defined our unit type. Now we need to, it asks us a question for the kind of the sensor. So whatever is wired, we are going right to left from within the device, the application programming data type, and then we get out to the port analog and input markers. Then we get into the unit type for conversion. Then we get into the sensor. Now, within the sensor, let's say we install 10K 10K resistor, and we will add this. Now, this was the second layer completed, and the third layer of compound markers are added within one record. Now it's asking us linear conversion curve, the table that you were mentioning. We are actually doing that by tags. And for that, this is going to ask us a bunch of other tags. So what we have done for that is that we have basically a list of tags that you can add at once. So you can see that we have thermistor 10K, low is 92, high, max, min, max val, offset, and unit. So if I click on this, what this is telling me is that, hey, these tags are not added, please add it to the device. So I will hit save. Now we have basically completed our definition of tags, but there's still some tags that we still need to add for the engine to process this. And those tags are row and cur. What this means is that there's a row data coming from GPIO, and we will have a conversion to a cur data. We will have a Sedona ID and type. This is a placeholder so that we can expose the Sedona slot ID back to haystack, and we can expose the Sedona type back to haystack, which you could use it for other reasons. And also enabled. Enabled is basically enables GPIO to read the data from raw data and converts it and passes it up. So this will be good enough to get the data to a raw data, to a curval data, but still there's one thing missing, is the utilization of haystack tags. So what we will do for this is that we will add our tags markers that are defined. So we can just go here, zone air temp sensor, and we have a bunch of tags here. In order to remember how we are going to search it within all the tags are in here, we just create a point query placeholder so that we would remember how we are going to search it. So here's zone air temp sensor. As you can see, this is red. Where we saved it is right now, we saved it in the SkySparks folio database. And we can actually post this to the Sandstar Layer, which is completely open source. So what we are doing now is that we are literally adding a record to the zinc file that is within the device. So what I will do is I will add this, save, adds it to the memory, commit dumps the file to the zinc file, and restarts the Sandstar's engine so that it would load correctly within the system. So if we were to go to the EAC config and device config, we would see the device zone temp added to the zinc file right here with a parentheses 4. So we literally updated the database template based on a haystack REST API.
That's cool.
So also you see that it was red. Now it is all green, and we can see it here. And we can also just go to the live model, and you can see that we have the data here, and we have the data within the live model. So let's do this really quick. We're just going to go into EAC config, Sandstar. We're going to stop the Sandstar engine completely. We're going to start it back up. So this is started, and we can see the status as on port 8085, we have the haystack running, 1876, which is the year that Sedona was incorporated, where Brian had a vacation.
Oh,
and Sedona's web service port is 8080. So now we can get into the SVM engine and see the benefits of what we have built in here. Anything that you would like to add here, Kelvin?
No, not right now.
Okay,
that's
so
really cool.
Let's dive into Contemporary Controls Editor, which is free to download, I think, if they're still doing it.
Yeah, I want to make a comment about that. This is a really cool thing. I mean, there might be something else that's similar, but this is the first DDC programming tool that you can program any Sedona device with that I've seen. I think there's some others out there, but this is the one that, I mean, you could just go get it right now. You download it, and just as long, if you're really Sedona savvy, just as long as you have the manifest for the kit that you're trying to connect to, because once again, the abstraction, like the kits, as long as you have that manifest and you just throw it in the manifest file, you can connect to any Sedona device. And Contemporary Controls is really cool to make this, because like this is one of the only ones that I know of, DDC programming tool where you can program anybody's controller that is a Sedona controller.
Yeah, so and if they are using the SVM 1.28, Sedona version 1.2.8, then yes, you can definitely program it with it.
Yeah, that's why you're using it right now. I mean, you didn't have to go to Contemporary Controls to get like a special copy of it because I mean, Contemporary Controls makes their bass control controllers, which are really nice at a great price, right? But you don't have to get a special programming tool. You
don't have to pay for it.
You have your controller.
It's all out there, and it's free.
Yeah, you put your manifest in there, and then you're off and running.
Kit's in there.
Yeah, that's cool. I like that. Thank you, Contemporary Controls. That's cool. That's the future of our industry.
So in here we have one kit, and this kit is basically defines the Sandstar's EACIO kit. So this is the it is just a generic branding called Edge Analytics Controller IO, which runs the Sandstar. So we can drag and drop an analog input. Now, we don't have an analog input hard-coded to 1 or input 1. What we have is basically we have a point query, and within the point query, we can just type zone, air, temp, and sensor. What this will do is it will make a data call to the engine with these tags. And if it exists, it needs to exist only one. It has to be unique marker groups. And if it's 1, then it is okay, and it will give us the channel number and the value for that given system. this is basically the overall understanding of the Sandstar engine. I will show you one more thing to explain viewers, but if I see anyone doing this, I will be coming after them. What we can do is actually, there's a tag on this channel record or definition called channel and 4. Looking at zone, air, temp, and sensor is same as looking at channel equals 4 number. So this is how the existing VMS controllers hard code their systems to a system call, and you can't really change it. What we have is we look at all the tags that are within that grid, and we basically get to channel 4 and then read the rest of the data. Okay? So we can do more things with this. Let's get into a little bit more deep into the application layer. There is a cool folder, and I will explain you what is happening here. So there is an object called record count, and record count is looking for 2 tags that are type marker, and those are cool and command. And what this is saying is that within the engine, there is only one channel defined with cool and command markers. And the record exists. So what we do is we enable our loop for cool demand based on this tag. And we basically get our CV, our set point, as well as our room temperature. So the room temperature is not linked right now. We can actually link it from here. There's no sensor installed on our controller, but you will see that it's linked to 303 right now. So this is our room temperature control value, and set point is linked to an analog value. Let's take a look at the analog value really quick. We have an analog value defined in the controller within the record editor as a AV, and it has the tags called zone, air, temp, sensor, occupied, cooling. So it has all these tags in there, and we basically can expose the set point to the REST API calls, and we will get back to that in a second. Within here, we have the query size 1. So our number of outputs within linear sequencer is set to 1. And our binary output, we have cool command stage 1. It's on channel 35. And we have cool command stage 2. And it doesn't exist. It doesn't hurt us. We can have all of our binary outputs listed within this cool control. And it will basically read it. So let's do a trick here. What we are going to do is we're going to go ahead and add a cool command stage 2 to our engine and see what this will do automatically for us. So what we're going to do is I'm going to go device template. So let's search for digital output 7. Let's check for 50. If there's anything with a 50 within the database, there isn't. So this should be fine for us. So what we're going to do is we're going to add it to channel 50, and we're going to add cool stage 2. Hit OK. In here, I'm just going to go a little bit quicker. So this is going to be a bool binary output save. Now it is going to be enum, and the enum is going to be cool SDG to on, cool SDG to off. We hit accept, we hit save. Pretty much we have our engine almost ready. We just need to add our enable tag, roll cur, and Sedona type. We hit save to this. Now we need to upload this to the engine. So we do commit to Sandstar, cool stage 2, add, and this will basically turn to green. And let's check into our engine here. This needs to, I think there's a little thing that we need to update here. It should automatically update this every other 5 seconds or so. But for that, what I will do is, just to make sure, I'm just going to stop the Sandstar. Let's save it here. I'm going to stop the Sandstar and restart it. Stop. Stop and start is pretty quick. It's not, it's a small application. It only uses like 5 megabyte memory. It is not using a lot of memory within the application.
Yeah, you're not restarting the platform. You're restarting a process on the platform, right? I mean,
that is correct.
Yeah, which is, that's another issue with operating systems is, sometimes these controllers take a long time to boot up.
Yeah.
But that's not the case with Sedona, because you can actually, stop, if you design your platform that way, you can stop the virtual machine, restart it again, and then, by extension with Sandstar, you can stop this code running and start it all over again.
So one step that I forgot, I'm getting excited here, is adding the cool stage tags. So there's no cool command stage 2 tags here. So I need to add that. So we'll just add this, and we will generate the marker list so that I would remember on how we search this. And you can see that this is a good demo for troubleshooting as well. You can see that all these other tags are within the Sandstar engine, but the ones that I just added is not there. So what we're going to do is we're going to go to the Sandstar. We can just select the cool command 2, which is 50. We can delete that. We can go back and add it to the engine. Now we can check our engine here that has not got invoked yet. So we are going to restart the engine. Let's just make sure that these are updated. So let's just do from here. I'm just going to search for cool within the live view. Stage 2, delete. We're going to go offline view. We're going to add it to the Sandstar engine. We are adding a channel. So we can go back here and look at it, and it looks like it is synced in full. Yes, so it is synced. Let's go to here. That has not been updated yet. So what we are going to do is we are going to restart our engine, because I had forgotten to add those tags within the system. So we can go to the service. Cool. And now you see we have 2 points with a cool command, and our number of outputs is turned into 2. And you can see that my channel for cool command stage 2 is on a separate port. So the Sedona code, when we save this to a PC, it is pretty much abstracted from everything else. From where it is wired, how it is wired, which controller it is completely abstracted from the application, from the hardware. So there's another benefit. The other benefit is that we can have all types of applications. We have written a cycle folder, and the cycle folder has an input. If you want to cycle it, if it is true. If you don't want to cycle it, you can set it to false. And within the record count, you can put the economizer set to it is 0, so record doesn't exist, it is false. And you can link this back to the point folder here, to the cycle folder. And that cycle, that branch of the code, does not get cycled. It's not even a part of the Sedona engine, cycle app engine process. It is completely abstracted out. There's another benefit. This one, I actually want to demonstrate it and create it together. And there's an analog output within the engine, and it is called air command damper outside. So this is our outside air damper command. And we usually have within our systems a minimum requirement for this. And we could change this minimum requirement based on other sensors. Other applications could send us a data based on tags, and that requirement might change, and you might want to change this requirement. So for that, what we have is exposed tags. So let's go and look at this channel in the live view editor within the record editor. So I'm going to close our window that is split into 2. We'll go into live view, and we will search for outside damper. So this is our outside damper command that is in live, and our cur value is 0.8, which means 8%. And what we are seeing is that within the record itself, we have a tag called minimum outside air set point. So I can just copy that, go back to the engine. This is exposed tags. And we are going to link the channel to the channel object. And within the tag, we're going to look for the minimum outside air set point. Within our application, we basically write 0 to 10 volt VDC. So what we want to write is we want to write 8%. So I have this little logic that is located here, and I can write it back into the controller to the output. So as you can see that we are writing 8, our output is 8 volts, actually 0.8 volts, less than a volt, which would turn on the system 8%. Okay? Now, what is the benefit of this is this. We can go into record editor, and I can just change this to 12. And we are actually writing to that tag live through haystack REST API calls. So if I hit save, we go back to here, and you see that it's 12, and I'm writing 1.2, which equals to 12% damper open. So with REST API calls and tags, we could actually control our buildings much more efficiently. And we can actually bring new era of programmers who understand REST API calls and reading data and maintaining data. So I don't think I've seen anything that is open source that is way open with REST API calls where you can invoke a system like this. And this is basically one of the main features of Sandstar, so that you can change your systems with REST API calls. So in the future, there could be open source applications for mobile apps which could read the Zinc file here and create like a mobile app directly reading the real-time data. As you can see, we can see the curval here as well. We can see the point status. You can write apps that would define your ports with mobile applications. Because it is already open, you can differentiate yourself within the industry. So overall, this is all the features we get by having Sandstar and tag-based control.
Would you say that it would be possible to, and I've heard people talk about this before, and people have tried to come up with programs and schemes to do this, but would you say that this would make it possible, at least from the device level, you can't do anything unless the device can do it, but possible, like say you have things like PI loops, like stuff that is out of tune, like you have to start from the very lowest level. Like if you want to optimize things, the hardware has to be capable of talking to something that can make that analysis, right? And so would you say that this is something like this is the beginning of being able to analyze equipment, and then for that data analytics system to actually be able to implement the optimization? So you might have like drives or valves or things that are out of tune. If you wanted an analytics system to be able to actually fix them,
or optimize them
like this, right? Would you say that's a true statement?
This would be the stepping stone where it would get us to implement I want to call reinforced learning or machine learning, or this enables us to create the digital twin for reinforced learning to see how a system is reacting. And then it could update the slots that you see right now. There's a loop and it has slots like KP, KI, KD. It could update those parameters after it plays it within the virtual twin in the cloud. Yes, so my understanding of your question is that could we optimize DDC by analytics and applications? Would this enable it? Yes, it would enable it. And that's one of the main goals of Sandstar achieving. And even if we wanted to do machine learning or reinforcement learning in cloud, create a digital twin, those things are not cheap either. The engineers who work on those, their yearly rates aren't low numbers. So having a DDC that is portable will enable us to have enough data for us to acquire and implement such a feature. And I'm sure there are open source libraries out there, especially I think I heard TensorFlow, it runs on a JavaScript now. And if it's running on a JavaScript, TensorFlow, we can link this to TensorFlow with JavaScript. So we don't need an embedded code. We don't need a database code. We can directly link this code to JavaScript. If you look at it at the end of the day, this record editor is a JavaScript application. And from this JavaScript application, we are able to add and define and delete records from the grid within Sandstar, meaning we can delete a channel, add a channel, update a channel. We can actually update a tag within a channel. So we can do everything that is needed from us to define the DDC code parameters. So your statement is absolutely correct.
Yeah, I mean, we open the news and the internet, and a lot of these, there's a lot of buzzwords around, IoT, AI, machine learning, like you go anywhere and like these words just get like thrown around.
Mm-hmm.
But it's a real thing. I mean, it's possible, and you have to start from the ground up. Like, if you actually want to end up doing this stuff someday, you want your systems to do this stuff, it starts at the hardware level, because I mean, analytics and data, it has to start at the edge device, right? There's another buzzword, right?
Mm-hmm.
The edge device has to be capable of having these changes being made to it in a secure way. Obviously you don't want anybody to come in here and start like turning your equipment on and off, so security is a big issue. So the hardware has to be capable of doing all that stuff. If you ever want to do the AI, if you ever want a machine to decide what's best for a building, the hardware has to be there first, or else it's never going to happen. It's a crap in, crap out. You're not getting good data. You're not going to be able to do anything with the equipment. And
absolutely.
Yeah, and the key is that with Haystack, right, is to get everybody to agree on what the names of stuff is. What the name, what we should call things. What should we call a temperature sensor, right? That's a great idea. That's it. That's where it all starts. Is standardization.
Yeah, and within Haystack, there's an operation called nav, and one of the navs that we completed already is that we are able to, and which will be released within the next couple days. We completed it today. We are able to expose all these definitions to the nav so that you can see what is in there. There's also another nav that we can create, which is somewhat called dynamic navigations. We could actually expose all the Sedona layer components to the navigation, so you can actually subscribe to systems within the application. And you just saw Kushal posting a message about the navs right while I was doing the video. That was great. So we are able to do the NAS for the zinc level items, and we can actually expose the points within the slot level as well. So actually, I would like to show you in Haystack. Within Haystack, we will basically do pretty much the same thing. I'm just going to open up Haystack nav. So Haystack is open source, that's within Niagara. And there's basically a CP site space. This basically defines site, equip, and points within defined in Haystack. And then you got the component space, which is the slot. We are going to implement this if there are any programmers who are good in C++ and what would like to get involved with programming the slot nav space, we are happy to have them join us on implementing the slot space. Since we don't have historical data implementation yet, we don't need the navigation of haystack ops for historical space. We have already got finished the SCP. So in our system, it will be DP because we call it device endpoint. We don't call it equip endpoint. So we basically have a device and a point within the Sandstar architecture. And that gets converted to equip endpoint within analytics engine. You can have multiple devices controlling one equip. That was our thought process within that. So let's end this conversation with an action item together. So action item would be join us defining the tags like minimum outside air, set point, and other tags that could actually be a part of the logic engine. Just join us under Sandstar working group so that we can define different tags for different applications. So tags would talk to other devices. Based on tags, we can change the modus operandi, or we could have metamorphing DDC code within the DDC controllers.
That's a question I have. So how are we're gonna go about this? I mean, obviously there's interest there. There's people who have joined the group. What's next? You're gonna develop a list of different things that need to be done, and then are you gonna accept volunteers, or how's that gonna work?
So I think there will be multiple parts of volunteers. One of the volunteers will be PE or mechanical engineers who define these systems and who want to get involved with open DDC systems that are part of the tag-based control, which is a new way of doing things. Those companies would get involved here so that we would define tags that are related to control. The other tier of working group members would be people who are programming savvy, who would help us with programming. And last not the least, there will be people like you and me who would work on documentation, marketing, testing is really important for it is very involved process of testing, but we are trying to simplify it every day with simple scripting to compile and run on a system, and documentation will be a very important part of the process as well. So we will be posting it here. This video is the first of its kind for calling and explaining what it is, how it works, why we are building it. It will give people idea of why we built it, and we will basically start talking within this working group and hopefully people will get involved within it. So
great. Yeah, looking forward to it. Looking forward to helping any way I can. You know, I'm not a coder. I'm not. I'll help any way I can. You know,
you're the first person that compiled it on a BeagleBone. If you want to show everyone where it is running right now.
Oh yeah. So I mean, just to kind of give you an idea of what, you know. So this is a BeagleBone black. It's not black. This is a version from Element 14 that they came out with industrial temperature rated components, right? So what I did was all the instructions are there. If you click on the links, basically just go to the link there's a bit bucket, and then get yourself, if you already have a BeagleBone, grab it. Get yourself a fresh micro SD card, and download the latest Debian Linux image from the you just Google BeagleBone latest images. Get the one at the very top of the list. Download the thing. Use all the standard instructions to image the card, which is pretty easy. If you like Raspberry Pis, BeagleBones, it should be pretty easy to do. Put the latest image on the card. Take your BeagleBone, plug it in, turn it on. Log in. You don't have to log in as root or anything anymore. Just log in as Debian, and then and follow the instructions, and all the files will install themselves. So you just a couple commands, it'll fully install all the files. And then once the files are installed, what you're going to do is, if you're familiar with Sedona, if you ever built it yourself, basically there's a bunch of Python scripts in there that basically do everything for you. You just run a simple command, and it's going to build everything. So I mean, not only are you building the Sedona virtual machine, but you're also going to build Alper's source code, which includes the C++ files for haystack. So if you go on haystack, there's the haystack C++. It's basically an adaptation of that source code, that was combined with so you had the two different pieces of code. You had the C++ and the C, and what Alper's done is he's integrated it all into a single build. So remember, it's not going to build as fast as just the Sedona virtual machine by itself. That was one of the mistakes I made. I almost accidentally pulled the plug because I was just getting impatient. But the code will build, because it's got to build all that haystack code. So when you build it, go grab a Coke or something. Go check your email. Come back. The thing's going to build. Once it's all done, then you're going to run the Sedona virtual machine in the same way that you've always done. You're going to navigate to the folder where the actual application is. The actual sob file is already going to be in there. And then you run the command to execute the platform, which is dash plat, right? So you're telling the Sedona virtual machine to run in platform mode.
Mm-hmm.
And it's going to run, and it's going to start all the haystack threads and everything, and then you'll be up and running. If you have the Contemporary Controls application editor, all you have to do is take the manifest file for the EACIO kit that you'll see in one of the directories. So like, if you're familiar with Sedona, you go to your manifests. All you do is you take that manifest XML file, you toss it in the appropriate folder in the Contemporary Controls directory system, because once again, that's all you need to connect to any device with their open programming tool, and then you can connect through socks to the device, and the default password is admin. No password, and you'll be in there, and you can see it up and running. And of course, all the source code for everything is all included in there. So if you want to, like the first time I talked to Alper was, I don't know what, like a couple weeks ago when you announced it. So I mean, we've only known each other for a very short amount of time, and I went in there, and like I said, I'm not a coder. I can read code. I just started digging in there and looking through all the source code, and I was like, wow, this is really cool, and then I built it and ran it. So I mean, you don't have to be Brian Frank to get this thing up and running. You can just be somebody who's kind of just interested in
yeah. So I would like to add on top of it, to basically, nobody wants to add and edit a device config manually. It's almost ridiculous to do, and we have already written application called Visualtech for the last 2 years, and we just ported some of that code to write record editor. So record editor is almost like a must to be able to play with this application, even if you have your own devices, unless you want to play with it in CSV editor and then save it as a zinc to that certain folder where it goes. For that reason, you could actually download record editor from Stack Hub. It is free. There's no licensing to it. There's no limitations to it, pretty much. So if you go to record editor, you can just download this. You could buy SkySpark from anyone. This is not a sales call at all. And install this. You can buy SkySpark as low as 10 points, which is like $60 at least. So you could basically buy it and play with it and install it with the record editor on it. And the idea of that would be is that you can edit these Zinc files. And from there, you can define everything and generate the tags and play with it and build your own capes and build your own devices. And this would be the best way to get started, pretty much. So,
yeah.
Yeah, I think this was a great call, and I appreciate everyone listening to this.
Yeah, this is really cool, Alper. I mean, I'm really impressed. You know, like I said, we just met, but like, yeah, I mean, this is awesome. You know, and obviously there's a lot of work to do, and yeah, anybody like I just randomly approached you, right? Like, hey, I'll help. Yeah,
exactly.
Totally what needs to happen in our industry, in my opinion. Like, I really think that something like this is what we need to do to like make our industry, you know, go from something that's really kind of specialized to something that is in every single building. That's the reason why I'm doing this. You know, it's like, I think that I want to increase the size of our industry. I want to increase DDC control. Because, I mean, you know, it's a struggle. Like, you know, sometimes people say, like, oh, this is just too complicated. Let's just put package units. Let's just put VRF. You know, who cares if graphics or analytics or any of this stuff? We don't want any of this stuff. We just take the easy way out, right? But then, you know, if you put this stuff in here and people see the value, because there is value there. You know, there's energy savings. There's occupant comfort. There's all kinds of benefits, you know, kind of like at the point where it's like, hey, should we put chillers in buildings? Nah, let's just open the windows, you know? Like at some point somebody realized, you know, putting a mechanical system in a building is better than, you know, just and ventilation is better than putting, not having any conditioning, because you could do that too if you wanted to. You know, you can live in a tent if you want, right?
Yeah, right. Right now, within the systems that we do, we have we do resets for outside air temperature, right? And usually those resets are done with hard-coded links. Now we could actually, if you think about it, because we will have these tag-based systems, we can create more complicated resets for any kind of reset. It could be outside air temperature, air quality resets, discharge temperature resets. We could create any kind of reset because these devices could talk to each other tag-based, based on a certain reset, and it would write to multiple devices. At that point, we can bring new programmers to like it, because these are the type of programming that new era programmers like. REST API calls is pretty much what all programmers do lately. So I think we would bring more technical programming savvy engineers to our industry, which I think we are lacking a lot right now.
I agree. One last comment, from me. Every time I go into the store, the Home Depot, the home automation IoT section is just getting larger and larger, and it's kind of interesting to see, like, you know, Amazon and all of these people, they're investing heavily in these technologies, and they're kind of doing it in parallel to our industry. You know, they haven't really moved on to the buildings yet. It would be it would be a shame if that train took off without us. You know, the people who've been doing building automation before they were using the term IoT. You know, I mean, they're kind of figuring out their own stuff on their own. They have their own protocols. You know, they've got MQTT. You know, they have their own devices. They have, you know, Echo, Alexa, Nest thermostat. All that stuff is kind of developing in parallel. And, you know, we want to, instead of them having to reinvent the wheel, attract those people into our industry, and, you know, just one huge thing just develops all together, you know, instead of...
Within that term, you know, Google Nest actually had the Thread Wireless, which is actually getting into our industry from home automation. Thread Wireless was built by Nest, and Google also open sourced another project called Google Weave, and that also has tag-based, but for car door openers, and it's not as convoluted as haystack, but it's basically for opening doors and things like that. So there's a parallel things that are happening in home space, and maybe in future companies like Google would see project Sandstar as a valuable, and maybe they would implement haystack within there instead of doing Weave or other implementations. But it's the same thing at the end of the day. And you're right, there's more devices out there coming up within the home automation space. Why not have devices that are temperature sensors that can hold history, that would say how much data it has and pass data when it's needed? I think that's when our industry will get excited, and hopefully we'll do really good within the marketing of Sandstar, and people will listen to us, and we'll...
Yeah, and it all starts with standardization, you know? Yeah, you have to have a foundation to build everything, right? Yeah, really cool.
Thank you, everyone, for listening to us. It has been a long meeting. Thank you.